development. I'll show you an example of that, and have a discussion of fuels. How many people have seen the modern versus legacy video that Underwriters Laboratory put out? I'd say you're making pretty good market penetration there, Steve. And part of the reason of that, you know, there the boxes were the same. The big difference is the fuels, and we'll talk about that for a little bit. Flow paths and neutral planes. What makes hot gas move the way it does? What decides where the hot gas is going to go within a structure? We're going to talk a little bit about that. Flow paths. Wind impacted fires. Again, it's imparting pressure to the building. It's potentially sealing off a low pressure vent and injecting more energy into the structure, as well as additional oxygen. And last but not least, the importance of size up. So why is fire research important to firefighters? Well, you fight fires in all kinds of structures, and as you'll see from some of this assortment of pictures, the researchers have ignited fires in all sorts of structures. 16-story high-rise buildings, 7-story high-rise buildings, old high schools, brick row homes, modern construction townhouses, in non-windy conditions and also in windy conditions. So we've tried to examine the gamut of conditions that you work under to get a better understanding of how that fire behaves in the real world under conditions that you have to deal with. So we have that one piece of what kind of environment is the fire going to provide and present you that you need to deal with. Now the other side of that equation is what tools and technology do you have to counter the effects of the fire? Well, you have an SCBA to protect you from the toxic gases. You have turnout gear, PPE, to protect you from some of the heat for some period of time. And it's not all that well defined what those periods of time are. And so we do a lot of testing at NIST to look at the heat transfer through turnout gear, to look at what will fail a face piece, to look at your electronic safety equipment and what its capabilities are and also what its limitations are. So again, pretty important stuff to you. Last but not least, we've been developing a body of knowledge since the 1990s, both conducting full-scale structure fires in Phoenix, in Toledo, Ohio, Chicago, New York, Spartanburg. We're collecting a pretty good body of knowledge. Another big feature that NIST does with their mathematicians and their programmers and their PhD scientists is the ability to try to predict where the fire is going to go with a computational fire model. And so between the fire models and the fire experiments, we've really gotten a better understanding of fire behavior in structures, how the fire moves, what the flow path will be, what causes the fire to move. Unfortunately, many of these opportunities are generated by firefighter line of duty deaths, right? And that's in many ways what's driving the studies. We need to understand why this happened to this firefighter. Why did this experienced captain die in something that from the street looked like an everyday bread and butter, nothing fire, and yet he didn't go home to his family? So we're gaining a lot of insight there. One of the biggest pieces of information that's getting in the firefighter training manuals now is that fire doesn't always behave the same way. For decades, firefighters were taught that there was an ideal fuel-controlled model where you had ignition, growth, a fully developed fire. That fully developed fire may have transitioned through flashover or not, and then the decay would be caused basically by running out of fuel or suppression. Well, that's not how houses work today. Houses are wrapped in plastic. They have multi-pane windows. They're heavily insulated. They're trying to limit the amount of air that goes in. The fuels that are in our houses today need a lot of oxygen for complete combustion. So what happens is we end up with a ventilation-controlled fire or a fuel-rich condition very early on. The fire grows. It tries to go to flashover, but it consumes the oxygen that's stored in the house or trapped in the house, and then the temperature drops significantly. The fire darkens down, if you will. That would be what you would see. And then with an introduction of fresh oxygen due to an opening of a door or a breaking of a window. The fire then accelerates, consuming that oxygen, increasing the heat release rate, increasing the fire hazard, and transitions to flashover, a ventilation-induced flashover. So let's look at one of these. So as you see in the lower corner, lower left-hand corner there, we have our idealized curve for a ventilation-controlled fire. I'm showing you the exterior view in the other lower corner, and we're looking at the inside. So we start off with ignition. You see that once we ignite that sofa, which is made of polyurethane foam and polyesters, you see that there's excess soot being created immediately. That excess soot means that there's inefficient combustion, and the fact that you can see the visible carbon, the visible soot, there's also other fuel gases in there that can burn. That's fuel that can burn later. We get into the growth stage. We have flame impingement on the ceiling. You can see that a hot gas layer, it's very thin right now, only about a foot and a half thick, is starting to grow in that space. And again, that contains heat and gaseous fuel, right? Two legs of the fire triangle. We go a little bit further, and the fire reaches its first peak. So pretty much the entire sofa is involved. The fire has spread to an adjacent chair. We have flame going up the wall, impinging on the ceiling. Smoke is starting to bank down. Smoke is filling the upstairs of the townhouse already, as you can see from that unidirectional flow out the upstairs window. But now it's consumed a lot of the oxygen in the space. It doesn't have enough oxygen there to continue flaming combustion, and it starts to darken down. So the flames at the ceiling at the peak were around 1,400 degrees Fahrenheit, and within seconds they dropped more than 1,000 degrees to 400 degrees Fahrenheit because the fire ran out of oxygen. What do you see? You don't see much. The house is full of smoke. What's pushing out the window from the exterior? Nothing. The gases have cooled down. They're no longer expanding and creating a high pressure. They're actually shrinking, and therefore they're not pushing out the window. In fact, we're sucking air in that upper window just a little bit. Now we're going to make a vent. We open the front door. Once the front door is open, you see that within 5 seconds you can see flame again. Fresh air rushes in the lower part of the front door. The front door is serving as a bidirectional vent with high pressure hot gases coming out the top and the denser, cool, fresh air being entrained or pulled by the fire in low, and the heat release rate starts to grow. In about 80 seconds after that door was open, the living room area is post-flashover. Fully engulfed in flame, floor to ceiling, temperatures in excess of 1,100 degrees. You can see the amount of smoke pouring out of the upstairs window, and now we're at this fully developed fire. So you can see how rapidly, within a time span of less than 2 minutes, it went from a fire that was going out to a post-flashover fully developed fire, just by changing one vent. Well, part of what plays a role here is that the fuels are different. And here's a demonstration you can do back at home. I wouldn't suggest doing it inside, but maybe outside on a picnic table. Take a splinter of wood and light it with a candle. And you'll notice that it burns pretty clean. We don't see a lot of excess soot coming off of that flame. Now take a piece of expanded polystyrene, or in other words, cut a sliver off your foam coffee cup. And be prepared to let go of it quickly once it's ignited, because you're going to see how rapidly it burns. And what do you notice in that picture? There's a lot of excess soot, a lot of excess smoke, excess fuel that's not being burned. And the reason is that polystyrene would like to have a lot more oxygen to burn efficiently. Flow paths. So basically the flow path is the volume between an inlet to a structure and an outlet. It allows the movement of heat and smoke from a high pressure area within the fire area towards a lower pressure vent or area that's accessible due to a window opening or an open doorway. In the single compartment case, it's fairly straightforward. We have a bidirectional flow in that open doorway. The firefighter crawls in. Cool air goes over the firefighter. That's a good thing. And hot gases go out over above the firefighter. Once we get into a little more complicated structure, such as the one floor of an apartment building there, you see that the fire started in one apartment there were windows open, and it spread down to the apartment with the windows open initially. And then once the firefighters made entry in the stair on the far right-hand side, the smoke and flames headed in that direction as well. Now keep in mind, there's such a high amount of fuel in that apartment that even though flames are showing from the window, which firefighters would say, well, that's a pretty good thing, we're losing a lot of heat, we're going to be able to go get it, there's still plenty of heat if the oxygen is available in the hallway for the flames to come into the hallway as well. What about if we have a two-story flow path? Well, you can see on the left-hand side, we have a basement fire that's been vented, and the hot gases are coming up the stair at about 15 to 20 miles an hour. Temperatures in excess of 1,000 degrees, but they may not be flames because it's ventilation limited, so the firefighters wouldn't have any visual cue or any red stuff to say, we need to open up our hose lines. And then we have a multi-story case, and as you can see just from the number of arrows, things start to get complicated pretty quick, right? If you open the bulkhead door at the top of the stairs, you got a vertical vent on the bulkhead door. You could have a window vent. You can have a vent open to the corridor, depending on what doors are chalked open in the corridor, to the stairwell. You could have bidirectional flow or unidirectional flow, depending on whether there's a wind or not. So it becomes challenging for crews to communicate with each other and say, we need to control the flow path. We need to understand what doors are open and closed to make sure that we don't put members in between where the fire is and where the fire wants to go, because that's a high hazard area. You want to stay upwind of the fire. Well, when you're outside and you first arrive and you're looking at the structure fire and you're trying to get a sense of what's going on, what stage the fire's in, you can start looking at the smoke flow and the fire flow coming out of the windows. So on the left-hand side, you see that we have a large window that has bidirectional flow. The blue arrow is going in, feeding oxygen low in that window, and the hot gases or the flames are coming out the top portion. And where that bar is drawn across, we call that the neutral plane. That's the interface between where the hot gases are coming out high and the cool air is going in low. Now, if you look at the window next to it with the red arrow, we see that the smoke is just unidirectional out. It's only flowing one way. That is an exhaust vent only. Now, the reason that's an exhaust vent only is twofold. One is that the bottom sill of that window is in the smoke. It's above the neutral plane. And the other issue is it's got an air inlet from somewhere else, right? So if you see a window that's just full of outcoming gases, that's telling you it's got air coming from someplace else. If we look in the other image, where the window on the front side of the structure, side A, you see that we have bidirectional flow on the front window and unidirectional flow on the smaller window on the side. Again, based on the sill height of that window being above the neutral plane. What about for a doorway? Well, if we look at the first floor fire pictures, we can see that we have a pretty well-established neutral plane in the doorway. We have heavy smoke moving out pretty quickly, and of course a gap at the bottom where that fresh air is going in and being entrained. And then eventually, if nothing is done to that fire, nobody cuts off the air, nobody cools the gases, it's going to transition to flashover. And we see the flames coming out the door, but we still have a neutral plane in that doorway. Then we look to the basement fire case. Can you see a clearly defined neutral plane at that open front door on the first floor? It's kind of a smoky mess, isn't it? Well, again, it's in the hot gas layer. Where's the neutral plane in a basement fire? It's in the basement, right? It's on that fire floor. What do you notice about the flames coming out of the basement window in that lower photograph? Unidirectional. That entire 30-inch by 30-inch window is filled with fire that's flowing out, that's exiting. What's that tell you? It's got to have an opening somewhere else to get air down low. So again, just by looking at where the neutral plane is can give you some ideas about what the location of that fire is. Another view of a flow path, and I just put this graphic up because I'm going to show you a wind-driven video very quickly, where we have air being pushed in the high-pressure side. We have the burn room being the bedroom, or the orange room at the top, the fire room. Goes down a 12-foot hallway past the target room, and then into a living room and then out into a corridor where one direction we have a vent and the other direction we don't have a vent. So needless to say, most of the hot gases is taking the path of least resistance and flowing toward that low pressure vent or that outlet. So again, high pressure goes to low pressure. So we have a 20-mile-an-hour wind at our inlet, which you see on the left. We have a plate glass window installed there, and when the fire impinges on the window and transfers enough energy to it, it's going to stress the glass and fail that. And in the corridor view with the thermal imager, you see that it's a hot gas layer, cold gas layer scenario until the window fails. And then we have an environment in that corridor that is not survivable by a fully protected firefighter for very long. The other thing to notice is that even with a 20-mile-an-hour wind, steady wind pushing in that window, notice that the flames are pulsing back out up against the wind. Why is that? Well, between the mechanical energy being pushed in by the wind, as well as additional chemical energy being generated by the fire due to the additional oxygen, it's overpressurizing that room compared to what it can vent out that door and into the corridor. And as a result, it has to release that pressure, effectively burping itself with those pulses of flame back upwind, balancing the pressure. With a real wind, not a mechanical wind, not a fan, we saw the same phenomena, again, just with a room and contents fire. So with the room and contents fire, you can see that with 25 to 30 mile an hour wind hitting that building, we have fireballs that are being pushed out of that window upwind. Did anybody see that on the news in the past 2 weeks? One of the ways we examined to deal with the high-rise fire was to introduce water from the outside from the floor below. This way the firefighters would not have to be, the attack crew would not have to position themselves between where the fire was and where the fire wanted to go. As you can see in the public hallway inset, the hallway is filled with flame. So we're going to call for water. And really all that is a bent piece of pipe with some attachments welded to it. They're going to introduce the water into the window, and notice what happens to the conditions in the public hallway. The fire's gone. A little bit of water upwind provides a tremendous amount of cooling. It takes the hot gases out of the equation. It's not the fact that there's a bed and a couple of chairs or a couple of sofas that have been burning. Your challenge is that they've been burning for 10 minutes before you got there. They filled that structure with gaseous fuel, and as soon as it's been preheated, and as soon as it can mix with enough gaseous oxygen, you're going to have that flame. And that flame is going to spread through those gases at a rate of speed that you can't outcrawl or outrun. It's going to be 10 to 20 miles an hour, even with no wind. You put some wind behind it, it can be even faster. It's important to stay upwind. So that was with New York, those experiments. We had an opportunity to go down to Spartanburg, South Carolina. Single-family homes. And here what we're going to look at is a little bit of size up. So why is it important to do a 360 in this kind of scenario? Well, if you just ran off the truck as the officer, or the engine as the officer, and are trying to make some decisions what to do, what do you see? Light smoke at the front door. Right? Are you going to make your decision off that, what the crew should do? Let's walk around a little further, and you have the advantage here of looking at a visual view as well as a thermal imaging view. Where do you think the fire is? Looks like it's in a back bedroom maybe? Who knows? What's the visual view tell you? Do you have a clear neutral plane at the front door? Yeah, so something's inconsistent here. You need to keep looking. You need to keep thinking about what's going on before you make a decision what to do. Let's keep walking. Let's keep doing the 360. Now what are you thinking? Right? You're starting to see some smoke coming from lower parts of the building. You see some heat coming from lower parts of the building. And as soon as we get around to side Charlie here, it's going to be pretty obvious where the fire is. You'll also get a quick glimpse of where the neutral plane is. There you go. So we've got a basement fire. Basement's pretty involved. We have unidirectional smoke pushing out of the basement windows. We have air entrainment in that basement door. And you can see that the thermal signature at the front of the house has increased as well, just in the time it took to do the 360. So what are we going to do about this? Well, in this case, the decision was to take the first line and bring it around to the rear of the house, early water, and start flowing water as soon as possible. So as they get the line charged, what they're going to do is start flowing on the window on the D side and then work their way around to the C side. And watch the impact that that's going to have on the fire. We got a little bit of water in the window. What'd it do? Water's good. Seeing good conversion down there. Drops the temperature in the basement to about 400 degrees. Just with a little bit of water. What did it do for the flow path upstairs? Because the front door was open, we might have had firefighters crawling in, making entry on the front door. Well, the firefighter, if they were in there the whole time, the exterior shell would be getting up to about 300 degrees. Putting water in the basement reduced their turnout gear temperature to 200 degrees on the outside. The heat flux that their turnout gear saw went from 3 kilowatts per meter squared to 2 kilowatts per meter squared. This is all good. Things are dropping in temperature. You'll see that the temperatures in the living room went from 400 at the ceiling and 150 F at 1 foot to 200 and 100. 200 at the ceiling, 100 down low. Not steam temperatures, right? It's cooler than that. Conditions in the bedrooms upstairs got better. Conditions in the kitchen got better. So again, size up's very important. Controlling the flow path is very important. And to sort of sum up the decade of research, synthetic fuel's bad, but they're in everybody's home. So the hazard from the residential fire has increased. There's reduced compartmentation in many of the modern homes. Lightweight construction techniques, actually that engineered process allows that reduced compartmentation. Energy efficiency, all sorts of alternative energy measures are being brought into people's homes today that bring in different challenges. Something I hope you take away from this is that fire conditions can exceed the limits of your PPE. Right? So your face piece is going to start to soften around 300 F. Right? Around the same time your boards are going to start to droop and drip and all that sort of thing. And even though your gear can be exposed to flame for short periods of time, your gear can actually take a lot more energy insult than your skin can. So as a result, there's been occasion where there's gear that looks brand new that unfortunately had a firefighter inside that didn't survive because of the heat that got through the gear. The heat absorbs as much gear as it can, hot goes to cold, passes that energy on to you. Most structure fires you're going to operate in today are going to be ventilation limited. In other words, they're going to be fuel rich. They're going to be highly reactive to introduction of oxygen. Remember that smoke is fuel and that venting does not equal cooling. Size up, locate the fire, identify and stay out of the fire's flow path, out of the exhaust, account for wind conditions, stay upwind of the fire, look at alternative approaches to a basement fire due to potential for structural collapse as well as being in the flow path. What has always been taught for years, going from the on-burn to the burned, may not be the best attack. Sometimes it is, sometimes it isn't. Nothing here says always do something, with the exception, I guess, of the size up. The idea is to understand what that fire is doing, where is it, how big is it, and then make some decisions using the research as a basis for some of those decisions. Early water may be the very best approach, softening the target before you commit firefighter resources inside. And that may be the best approach not only for the firefighter's safety, but also for the safety of any occupants that might be viable in that building. Coordinated fire attack is critical for the effectiveness and safety of your fire crews. And with that, I'll turn it over to Steve, who will talk to you about coordinated fire attack.
Thanks, Dan. So what is coordinated fire attack? And Dan talked a lot about what flow paths are, understanding how gases move throughout structures. A lot of the takeaways from the research have to do with ventilation and how gases move. Then there's the suppression piece, the whole applying water, what happens when you apply water. But rarely do we put the two together. And it would probably be an understatement if I said, since the last big room session here, if there hasn't been some conversation about applying water, how you apply water, what it means, and the pushing fire concept, where's the heat go, where's the steam go? We're going to try and add to that a little bit. Have a quick conversation that many of us have had and many of you have had as you've gone around the country. In my case, I've had the opportunity to have this conversation in many places, and the different responses you get are actually kind of fascinating as you travel across the country. Start with this, what I would call simple, very basic scenario here, just to set the stage. Single family home, 1,200 square foot ranch house, fire coming out of the front door. Simple question, where's the line go? And there's probably 2,000 opinions in the room as to where that first line goes. I'll walk you through some of the conversation that we've had. Typically, it's two options. It's going through the front door. Those are the people that, for one of two reasons, either they want to get water on the fire the fastest, or they always go through the front door. And then there's the other group where I always fight the fire from unburned to burned. So I'm coming in this house from some uninvolved, unburned place, and I'm working my way towards the front of the structure to the front. Two varying opinions that we see quite a bit. And then we go ahead and we flip the scenario a little bit. Essentially, you take that house and you rotate it 180 degrees. Now the conversation changes. Now you have, where's the first line go? And the conversation goes one of two ways. Either I'm going to put water on the fire the fastest. That could either be going through the front door, going around to where the fire is showing from the Charlie side. Or it could be I always go through the front door. And the importance of this very simple conversation is, did your explanation for your choice between these two scenarios change? So if you had fire through the front door, and you are going through the front door because that's the quickest way to apply water, and now all of a sudden when the fire is coming out of the rear, does your explanation become, well, I'm going unburned to burned? That's a lot of what we see and a lot of what the conversation is. And I think the important piece here is, how quickly can you get water on the fire? It's going to be based on your resources, it's going to be based on your training, it's going to be based on your knowledge. But the important piece is that you have a reason for the tactic that you're choosing. And it is not because this entrance or this opening is closest to the fire truck. And I'll hear that as well. So I think it's absolutely important that we have a good answer for that. And my answer would be, how can you get water on the fire the fastest? It might be going through the front door, it might not be. If you don't believe you will push fire here, you can't automatically, because the fire is coming out of somewhere else, believe that you can push fire now. Let's talk about some of that. We can't separate suppression and ventilation. Both of those things are happening at the same time, so do we understand how they happen together? So we're going to walk through, again, a simple scenario. We're in the same house. We've got fire in the front corner of the house, AD corner, bedroom. We're going to do an interior fire attack. We're going to go ahead, we're going to open that front door. What happens when we open that front door? What did Dan just teach us? We create a flow path. We just ventilated. Our forcible entry created ventilation. Okay? The blue arrow there highlights the flow path. Fresh air is going in towards that fire. Hot gases are coming out, moving towards the low pressure, which is the front door. So as your attack crew makes your interior attack and starts moving into that structure, if they don't flow water, where's the fire going? Right over top of them, right? Right to the low pressure out of the front door. All right, so now to combat that, you're going to flow water. And we're assuming here that red cross in the back is a victim. When do you start flowing water? I'll get 1,000 answers as to when that is. The important piece to look at here is when you flow water and you have the ability to create steam and you have an ability to change or alter or impact that flow path with your suppression, it's important to understand how these things work. So if you flow water into that rear of the structure towards where the fire is, are you now flowing water between where the fire is and where the victim is? Really, not until you make the turn into that bedroom are you between where the fire and where the victim is. If you flow water in there and you create steam, where is the steam going? It's going to follow the flow path. It's going to the low pressure. It's coming back over top of your head. So we have the ability to have steam follow the flow path. Okay? We also have the ability to contract those gases by cooling them because water does a great job of absorbing energy. So let's walk through this. Now you have a second flow path. You now have a flow path out of that bedroom. So you pull up, you've got fire coming out of that bedroom, you're doing an interior attack. You come in, you start flowing water, you're in the flow path making your way towards that fire. As you flow water, where's the steam going? Following both flow paths. It can come out over you, and it can also go out through the window. So we start talking about coordinating ventilation, and we go ahead and we vent opposite the hose line. Steam is going to follow both low pressures. What do you want to do where you're at to make your side a higher pressure so that the steam goes away from you and doesn't come back over top of you? This door control is one way. Another way is we can impact that flow path with our stream. So if you are a fog nozzle person, or you use a straight stream or a smooth bore, what can you do to create a high pressure where you're at? You can either open up that fog pattern, or you can go ahead and whip your straight stream in a circular pattern, or make a Z, or make a T, or however you choose to do it, and create that higher pressure because you're entraining some air with your water, and have that steam move ahead of you. So we're impacting, the water is impacting the flow path, the fire is creating pressure. It's up to you to use your tactics to control it the way you want to control it. And if we're in a situation where we only teach one nozzle pattern to use in all scenarios, and we go back to the first scenario, and you don't want to make as much steam because you know the steam's coming back over top of you, do you want to open up a fog pattern, or do you want to rapidly rotate a smooth bore to entrain more air? No, because you know it's coming right back over top of you. But if you have a vent opposite you, now all of a sudden doing something like that makes sense because you're now forcing the heat and the steam away from you and out of the structure. What if we have a flow path going through the rear room as well? You start flowing water, where's the steam going? It's following all the low pressures. So if you have a firefighter that comes in, and that firefighter is where that cross is, and you open up a fog pattern, or you start whipping around a smooth bore, and you create more steam, and you create a high pressure where that firefighter is, the steam's going in two directions. It's going to go out through the fire room to the outside, and it's also going to move into the victim room. Right? So if you want to minimize that, what do you do with your stream? Keep it straight, right? Don't move it in a rapid motion to break it up, to move more gases, and to move more heat and steam. You have the ability to control these things. You can control the temperature of those gases you're crawling through until you make that turn, and the moment you make that turn, and that flow path to the victim room is now behind you, now what stream do you use? Whip it around, open a fog, because you want to create a high pressure between where you are and move everything to the outside. And this is the impact you can have with your stream. Now we're going to move to an exterior attack. That was an interior attack, and we can see there's some thought and some thinking that goes into the streams that we use to attack our fires and how it interacts with the flow path and what pressures mean. Now we're going to go to the outside. You pull up, you choose that the quickest way to get water on this fire is to apply water into the fire room where you see the fire venting from. So in this situation, you flow water into that room. Where's the steam going? It can only follow the flow path. It can only go from a high pressure to a low pressure. In this case, the inside of the structure is the high pressure. That fire created higher pressure in that structure. The low pressure is the outside. So, but if you want to minimize that and you want the steam moving outside faster, you want to use a straight stream or a smooth bore in a tight pattern off of that ceiling so that that steam has more of a chance to get out of that structure faster. Now we have a flow path back through the victim room. So when we get to that window and we want to knock that fire down, and we go ahead and we open up a fog pattern, or we rapidly move a smooth bore stream around or a straight stream around, where does the steam want to go? It wants to go to the low pressure. Well, if you're blocking the low pressure that is the fire room, where's the only other place it can go? Through the victim room. So you're going to move steam through that victim room. Are you going to push the fire into the victim room? You're not going to. You're going to take the temperatures in that room and you're going to drop them from 2,000 degrees down to about 200-300 degrees. But if you can use your nozzle skills and understand flow paths and coordinated attack and choose your nozzle pattern and your nozzle movement to make the fire behave so it's best for you and it's best for the victims, you have an opportunity to do that. This is where a thinking firefighter with a nozzle can accomplish what they need to accomplish very quickly. Can we get steam on firefighters on an interior attack? Yes. Can we get them on an exterior attack? Yes. Do we know when steam can move and when heat can move and when it can't, and it can only go from a high pressure to a low pressure? When we start understanding these things, we can start being much more effective as a firefighter for ourselves as well as for the victims. I'm going to show you a couple examples. A couple examples from Governor's Island. This is the floor plan of the fire I'm going to show you. 3 rooms across the side. Start the fire. You're going to have fire in the 3 rooms, or in this case 2 rooms on the top left corner. Fire starts in the middle room. We provide a flow path through ventilation into the kitchen. Where's the fire going to move? It's going to start moving to the source of the oxygen into the kitchen area. So now we're going to have fire coming out of the kitchen windows, and we're going to direct a smooth bore stream off the ceiling in that kitchen, and there's no other vent openings in the structure. So there's no flow path other than at that window. Where's the steam continuing to go? Back out against that tight stream. Fire gets knocked down, even though the original fire room was actually 1 room further into the structure than that kitchen was. Those gases get knocked down, that environment gets cooled quickly. Well, how much does it get cooled? We can measure things. We can start learning a lot more about this environment and the impact of our tactics through these measurements. The kitchen dropped 1,200 degrees, 1,400 to 200. Middle room dropped 300 degrees. Rear room dropped 200 degrees. And the hallway, which was completely away from the fire area, dropped from 550 to 300. So you can see by putting water where it needed to go and cooling off that environment, created conditions that were better throughout that floor, and the ability to keep the steam and heat moving in the direction that you wanted it to go allowed conditions to improve faster. That was with 14 seconds of water. Now we're going to look at water in the rear with a flow path. Same floor plan. In this case, we're going to put water through the rear windows, but we've got fire in all 3 rooms on that side of the structure. Fire coming out of the kitchen, fire coming out of the rear, and fire in the middle room. Watch the flames in the kitchen on the other side of the structure. No water is making it into that room, but you are cooling that environment so much, taking the energy out of the fire, taking the burning gases out of play, improving conditions front to back. And again, this is also important that if you don't want steam moving through that flow path and you want to minimize it, in this case, you wouldn't have whipped that smoothbore nozzle in a circular pattern. This was a big learning that came out of Governor's Island. We weren't paying much attention. Smoothbores, big ugly drops, long distance, good penetration. Until you start whipping them in a rapid pattern, all of a sudden, if you were to block the nozzle out, you would think that you had a fog nozzle on the end of that hose line because the water breaks up so much. So it's important to understand how these tools work, what's important, what's not important to your operation. Here you can see what happens with the numbers. Water goes into the rear room, 1600 degrees to 400 degrees. The middle room drops 600 degrees, the kitchen drops 500 degrees. Cooling off things throughout the structure. Putting water where it needs to go to absorb the most amount of energy possible, the fastest. Any victims in this structure, it's immediately getting better for them. And then, of course, timing matters. When we start talking about where you're going to put the first hose line and how long it takes you to get there, all of this stuff is an important part of the equation. There is never one answer for anything. There is no silver bullet. We need thinking firefighters to make the right decisions during these fires for the best outcome for the victims, the public, and themselves. In this case, you've got a fire, 3-story wood frame, fire on the top floor. Answer this question for yourself. How long would it take your members to get a hose line to that apartment door on the 3rd floor after your arrival? You could have an A-team, it takes 2 minutes, 3 minutes, 4 minutes, 5 minutes, whatever it is. What is the fire doing during that time period? It's not waiting for you. Temperatures are going up. Fire's probably burning into void spaces. Fire could be burning through doors, getting into victims that sheltered themselves behind closed doors. Could be getting up into the attic space. There's probably a few people in here that have made parking lots out of wood frame structures like this. I certainly have. Because you take that 5 minutes to get water on the fire. What if the pump operator could have water on that fire with the deck gun like this scenario in about 30 seconds because you trained for it and you know you can knock it down really quick? Where's that? If you're a victim laying in the back bedroom of that apartment, do you want water on the fire in 30 seconds or do you want water on the fire in 3.5 minutes? You want it in 30 seconds, right? Something to think about. I'm going to pass it to George. He's going to talk about implementation in the FDNY.
Thank you, Steve. So as Steve said, the FDNY has really partnered with Dan and Steve for close to a decade now, trying to improve and learn, and then take it the next step forward, implement. And we have implemented. And it's proving itself a valuable asset to us every day on the fire ground. The FDNY protects about 8.2 million residents and 50 million visitors every year. Tremendous obligation to protect those people. We cover 322 square miles, about 11,000 members, 142 truck companies, 209 engine companies. I know, it's obscenely large. But those 11,000 members all have to be trained. They all have to be educated. That's a tremendous undertaking. About 25,000 structural fires every year. 2,500 roughly serious structural fires. We're going to fires fairly regularly. Not every company every day, but we do go to fires. And it gives us a lot of experience. And that experience, coupled now with the science and the knowledge, is making us a better department. Why was this so critical for the FDNY? Look at these numbers. We did a little soul searching. We're trying to become what we call an HRO, a highly reliable organization, tracking small failures. We looked at a 25-year period in time in the FDNY's history, from 1958 to 1983. In that period of time, there were 202 line-of-duty deaths in the FDNY. 202 in 25 years. That's sobering. When we looked at that number, and we really boiled it down, we realized that 4 of those members burned to death. Can we think of a worse way to go on the fire ground? Burning to death? We didn't sign up to burn to death. So now we looked at 1985 to 2010. There was real good news for the FDNY in that period of time. Our line-of-duty deaths dropped from 202 down to 52. Kind of remarkable. But of those 52, 14 members burned to death. I'm not a math guy. If I was a math guy, I wouldn't be standing here probably. I would have gotten a good job. Right? That's what my parents think. 28% of our line-of-duty deaths, 28% were from burn injuries. We've got better equipment. A lot of us don't know what that equipment is capable of. Dan has given me a tremendous education. 300 degrees, our face piece, softening and failing. When you look at that modern versus the legacy, we blow through 300 degrees in the blink of an eye, in seconds. That's why the FDNY has invested so much in this partnership and in changes and embracing change in the FDNY. One of the first things that came out when we came up with that 14 number was, you know, we have our critics, and critics are wonderful. We love having the naysayers. We love having those questions because it forces us to improve. The initial knee-jerk reaction was, well, yeah, it's that bunker gear. Sorry to any of the manufacturers out in the room. We're too encapsulated. We don't know, we can't feel those changes that are occurring around us. We've lost the senses from our ears. We used to feel our ears getting hot, and we would adjust to that, we'd back out. We've lost that. That's not the answer. Because when we really looked at that number, we realized 7 of those 14 had bunker gear, 7 of those 14 didn't have bunker gear. Bunker gear is our reality. There's that Watt Street fire in Vandalia, triple line of duty deaths. I don't mean to pause, I have to. I know there are people in the room who are very aware of those incidents. And they won't look at me now. But Watt Street is why we have bunker gear. Because of the sacrifice of John Drennan, Jimmy Young, and Chris Siedenberg. They didn't die in vain. They forced the FDNY, or really the city of New York, who had been looking at bunker gear since the 1970s, to spend some money and get our members the equipment that we needed to protect them for the environment that we work in every day. Our workplace is the fire floor, the fire ground. We spend some time in the firehouse. Don't let the mayor know that. We do. I'm not going to lie to you. But our workplace is the fire ground, and the fire ground has changed and continues to change. It's dynamic. That's why we're continuing to test, and we're looking at different things. That's the critical nature of this work that's being done. It's been a long road. It doesn't happen overnight. We can't turn the ship in a matter of seconds. In 2006, we had several notable fires in high-rise buildings in the city of New York. Tracy Towers, Rockaway. I was the incident commander at a fire where we almost lost a member of the FDNY at a building that 10 years earlier had claimed another firefighter's life. Jimmy Williams, who died in 1996 at a wind-driven fire. That caused the FDNY to look and say, listen, we can't keep doing this. So we started by going out to Toledo, Ohio and looking at fans. And we went out to look at fans. Trust me, I wasn't on board, really. And we went to Toledo, we saw some very interesting things, and I started my education. And it caused us, through a relationship with the Chicago Fire Department, to go out and do some burns on State Street. And it got a lot more fun, because now we were really burning stuff. You know, out in Toledo, we were just messing around with cold smoke. And we started to realize how powerful these fans were and how they could assist us in controlling smoke in high-rise buildings. But we started asking more questions. This was all born from questions. Questions are great. Hopefully I won't talk too long and people will be able to ask a few questions today. Chicago. Then we went to Governor's Island and we did some burns on Governor's Island, looking at alternate strategies, wind control devices, high-rise nozzles. But we started learning about these things like flow paths. I started learning more about fire development. About 15 years into my career, I'm really starting to learn and grow and be educated into this. And then we did something else that was very important in the FDNY. We had what we called ventilation focus groups. We brought members of my department, no uniforms, no ranks, civilian clothes, from all ranks, from all corners of our department, very large department, and asked, what is ventilation? How is ventilation occurring on the fire ground? And we realized different people in different boroughs had different thoughts. My department could not start implementing change unless we really understood what was going on the fire ground. And I think that was a very critical point in our decision-making process. We went back out to Governor's Island, we did some of those experiments that Steve taught you and showed you. And then we started implementing it. In 2012, we did a series of burns, and by June of 2013, we started making changes. Formal changes that are in our books, and it's what the leadership of my department expects on the fire ground. We produced a document, Firefighting Procedures Ventilation. Ventilation happens at every fire, and we have books about private dwellings. We have books about high-rise buildings. We started formalizing our procedures back in the late 60s, early 70s. But we never had we have a book about engine ops. Who says we don't care about the engine, all right? We had a book about engine ops, but we didn't have a ventilation book. So now we do. When members enter this early decay stage, what Steve and Dan have showed us, very, very critical point in the fire's growth. The fire is starving at that point. And then we show up. Hopefully we get there before the cops. Because the cops get there first, they're on the hydrant, and they're kicking doors in, right? We have to control that vent, and that's what we're teaching our members. When members enter this early decay stage, they shall control the ventilation of windows and maintain control of the door to the fire area. These actions will limit the inflow of air. Steve and Dan mentioned, we open up that front door, we've just vented that building. We've just given the fire that vital oxygen that it needs to grow. We want to be mindful of that. We have to be mindful of that. Any change to fire conditions as the incident progresses or as a result of our ventilation tactics by our members must be communicated to the ladder company officer. We want the ladder company officer to know why, because when we looked at that 14 number, we realized that 12 of those 14 members were part of the inside team of the first due truck. or they were operating as if they were. It was one of them, there was a rescue company involved, there was an engine company officer searching ahead of the line trying to locate the fire. But these are the folks on the fire ground who are going to be in harm's way. Modern content fires develop rapidly, consuming the available oxygen. We need to figure out the science, folks. Fire is physics. Modern content fires generate greater volumes of heat and smoke that may overwhelm the vent points. When we start asking the engineers who help us, right? They're not designing these tests, they're working with us. They're our partners. How much do we have to vent? Because we want to vent more. Trust me, I've had, I think, 4 fires in my life, in my career, where I had a hose line in my hand. None of them were good. I didn't have the hose in my hand because I wanted it, or I took it off a truck. I had it there because it was given to me. We have to embrace this science. When we ask them, how much do we have to vent? They say, well, basically you'd want to remove like 2 of the 4 walls of that room that are burning to make it a fuel-regulated fire. I know some guys would like to try to do that, but we can't. They're awake, they're starting to laugh. A couple of them just went right over their heads, they just sailed, you know? Flow path, that movement of heat and smoke from the higher pressure within the fire area towards the lower pressure, towards those doors. Where do we normally operate? We're in the flow path. That's where we go, all right? That's where we go, that's where we are. We have to control that. Any operations conducted in the flow path will place members at significant risk. Our gear isn't really designed to keep us in the flow path. Show of hands. That book that comes with your gear, all right? It's like that tag that's on the mattress that says, on the penalty of law, do not remove. Who in the room has read that book? Yeah, not many, right? I read it about 2 years ago, I'm not going to lie to you. When a member of my department received critical burns that he's going to deal with on a daily basis for the rest of his life. And hopefully it's a long and prosperous life, but it's not the way you, I, or any of us should live. And basically, when you read that book, you know what the Cliff Notes version is? For the young people in the room, Cliff Notes is like Google, all right? And now they're really laughing. It's how I got through college, all right? The Cliff Notes version of that book is, don't go into burning buildings with this stuff on, all right? Bunker gear wasn't designed to let us go farther into the building. I think that's an unintended consequence of bunker gear. And trust me, I've crawled into a room and I've drooled and I've watched it. I'm going to wait for the line. I'm not going to close the door. I've done those things. I have a better education now. This is the education we're trying to give our members. Operations in the flow path will place members at significant risk. We have to go into the flow path. I understand. We have to be mindful of the vent while we're in that flow path. Very quick story. And that's a lie, because I really don't have quick stories. These guys laugh because they know me. I work with a lieutenant who's a really good guy, all right? He's got a little bit more time than me on the job, and he always had great questions. He was not asking me questions to try to poke holes in what we're doing, but he was asking me questions to try to understand. Every time I saw him, he had questions. So him and I have a fire in this building on this particular night. He's in the truck, I'm outside, clipboard carrying non-combatant. That's what Chief Galvin, the FDNY, says, right? I'm outside right now. Non-combatant with my clipboard. And this is what we have on arrival. Fire out the window, is that good or bad? It's good, right? That's what we were always taught? Not so sure anymore. Okay? But we can manage it. So crawls in, starts to do his search, goes to come out of the bedroom in the rear, searching the bedroom in the rear, and he realizes now fire is coming out of this room and it's at the top of the stairs. And it's actually vented the window on the D side or the 4 side. So now we have fire out both sides of the structure. And he says to himself, I'm going to dive down the stairs. And then he thinks, and he says, you know, I'm not a kid anymore. If I dive down the stairs, I'm probably going to break something. So I'm going to crawl underneath it. So I got my gear on. So he crawls underneath it, and he comes out, and he approaches me. The engine goes in, and they open up the line, and much like Governor's Island, in about 10 seconds, there's steam coming out the windows. I don't hear anything to the contrary that things aren't going too good. He approaches me in the street, and he says, Chief, I'm sorry to tell you, but I got burned. And we don't want our people burned, right? So I said, come on, man. You're kidding me. He goes, nah, my back. So he lifts his shirt up, and originally I don't see anything. But then when I get my hand light out, I realize he's got like a softball-sized blister on his back that's ruptured. And then he's got a couple other decent burns, okay? Nothing life-threatening, but he's not going to spend the night with his family or at the station. He's going to go spend the night in the hospital, okay? I don't want that. So we go, he gets the treatment he needs, and the next day I call him and I have a couple of questions for him. And after I ask him my questions, he says, I got a question for you, Chief. That's the flow path thing you've been trying to teach me, right? I said, yeah, absolutely. When I asked him how long he thought he was in that environment, those conditions, he said, Chief, it couldn't have been more than 4 seconds. 4 seconds in time, and he had third-degree burns. With his gear on, okay? I think sometimes we expect our gear to do more than it was ever designed to do, or certainly more than it's capable of doing. We have to be mindful of the flow path. This is nothing new. We do have a lot of testing now that's going on that was never done before, but there was discussions this morning about what went on in Iowa back in the 50s, right? Lloyd Lehman and people that were doing good work and had a good understanding. We're defining it a little bit better now. We're certainly communicating it better because of the ability that we have. Once a building is vented, the time for effective extinguishment is limited, since the fire will rapidly expand. Controlling the vent. As I said to you, the reason why I'm here is I was the incident commander where people almost died. So don't think of us showing another video as criticizing another department. I take plenty of criticism on my own shoulders. But we can see here, if we're not controlling that vent, we know where the fire is going to go. And it's as simple as closing a door. Something we should be mindful of. If we get to this structure and the civilian left the door open, or a police officer was kind enough to open it for us, while you're waiting for the line, shut the door. You're going to get a lot of bang for your buck. And then those little folks in the engine, quack, 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 right? They're all going to be following each other. They're going to come. It's okay. Come on with me. It's all right. Sorry, I had to do that. Right? Close the door. We teach civilians that, right? New York City has done ad campaigns. Just shut the door. But then the big dumb truckies show up, and we want to leave the door open because we want to see this. Controlling the vent. We can control the vent and still move a line in. Door control. The process of ensuring the entrance door providing access to the fire area is controlled and closed as much as possible after the search team enters without the protection of a hose line. We have 142 truck companies. We rapidly put truck companies on the scene who are going to search. While we're stretching our line, while we're doing those searches, we have to manage that vent. It is critical to the safety of the occupants and the members conducting searches that we control the entrance door until a charged hose line is in position to operate. A firefighter of the inside team must be positioned at the door inside the fire area to maintain control of the door until a charged hose line is ready to move through that door. We always said venting fire is good. You looked at that video that Dan ran with the wind, where you saw it go through the apartment. The same sort of thing, not to the same extent, happens without wind. Is venting fire really good? If we're not putting fire out for a prolonged period of time, is that really good for us? These two incidents, members are running out of air, maydays ultimately wind up being transmitted. The fire overwhelms the vent. All the bad stuff is not coming out. An awful lot of it is going back in. And we do see, more often now than I think ever before, where you pull up the fires out the windows, and it becomes a very, very challenging job. But when you look at some of the UL and some of the NIST work, you understand why. Because you understand what the temperatures are in the flow path, through that apartment door, where we're trying to mount our attack. All horizontal ventilation tactics, whether venting, what did I do?
I just told Shane next year.
Next year, you're on next year, Shane. Everybody, this is Shane, say goodnight to him. You went wrong too, my friend. Venting for extinguishment. We don't call it venting for fire anymore. That was the old term, venting for fire. And we know that was to facilitate the engine company's advance to an extinguishment of the fire. Well, if we're venting to extinguish the fire in the FDNY, that's what we call it now. Because we don't want to leave it up to interpretation. And we don't call it venting for life anymore. We call it venting for search. And we're putting parameters on our search crews that there should be a confirmed life hazard. Somebody at the fire scene saying, I know there's somebody in there. Not garbage pails in front of the house or a car in the driveway or the fact that the lawn's been manicured. Is the safest approach always from the unburned side to the burned side? Does this look like a particularly dangerous fire? Private dwelling, we do these all the time, right? A member of my department died in this building. Because we always had to go in the front door and down the stairs. We don't do that anymore. We talk about exterior hose lines. That was a cardinal sin in the FDNY 8-10 years ago. It was one of the 10 commandments. Thou shalt not put water into an occupied building. And then generally they'd mutter like a coward, go in there. No, not anymore. We've put this in our books now. A chief or a company officer should consider ordering an exterior hose line operated into a cellar window to allow for a quick knockdown. Quick knockdown. We're focusing on water on the fire. Let's get it there as quick as possible. That's a good thing. We're not as concerned anymore about where the steam, are we pushing fire, all that stuff. All right, we could talk all day about this. I want you to see the changes that the FDNY is embracing. The leadership of my department, 10,000 members strong, has decided that this makes sense. We even say if we're in the building, in an emergency, such as members trapped by the fire in the cellar or endangered by fire because a collapse has occurred, put water in the building. And we've had that. At that fire that I showed you where Rich Scalfani died, there was a line in the rear and they were asking permission to open the line. And it was a different time. We didn't know. We were concerned we were going to do bad things and we didn't do it. And that happened at a number of these fires. We've made those changes. In some situations, various factors, including the following, would preclude the descent down those interior stairs. High heat conditions at the top of the stairs, questionable stability, a serious fire condition. Fire out the window is a serious fire condition. We're telling our members now they can put water in those windows. A real-life situation. My mutual partner had this fire in Queens. The first line went through the front door. Heavy smoke. Does this look like a good fire? Yeah, what we call a good fire. The homeowner wasn't saying, oh boy, this is a good fire. We pull up and say, wow, this is a good fire, right? But we realized there was access in the rear. We got a second line around the rear. There were still members in the building. In the perfect world, withdraw those members? Absolutely. But how long is it going to take to withdraw those members? We've educated our incident commanders so they can make those split-second decisions to say, you know what, this is the right tactic for this particular incident. Now I'm going to send it over to, I left them time, all right, to my good friend Shane Ray. Talk about South Carolina.
Thank you, Chief. Good evening, Dan said we'd talk fast. I'm going to struggle with that. But for those engine company guys in the audience, we talk slow in the South and act fast. So that's why Mrs. Smith called us, was to bring the fire truck with water.
If anyone needs a translation, there will be subcaptions.
This is testing for you. I'm very blessed to have a great state with a lot of good fire departments in it that range from fully career departments to very small volunteer departments. And we're fortunate to have a good training delivery system across the state. And in doing that, the challenge is how do we take this information and get it to this wide audience? Well, naturally, we couldn't teach that in a traditional format. We couldn't take and put it in an instructor guide that would typically take us 18 months to write, format it, train all the 300 and something instructors we have across the state, the 400 fire department training instructors we have. It's like, so how do you get this information out? And we've done that in a non-traditional way using an online format that we'll talk about. But why make this change? I think that's one of the most important things. And when you look at the NIST reports, it may say that what role do we have? And I went to South Carolina to be the superintendent of the fire academy. But in that, I had to look at these, and looking back through all the years of studying these NIST reports, it said, what role do we play as training that says, as you see in these pictures, did we train them to act in this manner? Do we crawl you in a burn room that crawls you directly into the room? The one thing you don't ever do is put the fire out. What role do we play in making these changes? The other piece is do we blame something else? What part of the root cause did we really play in training? Did we blame it on construction? Did we blame it on the size of the structure? The firefighter got sick? Whatever the issue was that really the root cause? And that's where we took a hard look to say, are we really training our firefighters to do the right thing at the right time? And as Chief Healy said, one thing we knew for sure was do not let our people die yelling for water while we're scared to give it to them. Looking at the changes, though, we said, hey, we've had some success. So we had large career fire departments saying, hey, we did this, it worked. We had some say this training saved our lives. We had some small departments that rolled up with 2 people that said, hey, look at this giant structure we knocked down. And some other folks said, hey, when the dispatch told them to close the door, they were able to make a rescue. There was a lot of positive improvements made, and we said, well, if we don't want these people, and we truly mean the fact that we don't want them to die in vain, we'll take action. And that action will call for change. And that's what we've done. We've put it online. We've taken this online, working with the ISFSI, and I'll talk about that in a second, the International Society of Fire Service Instructors. Their opportunity to do a grant that said, hey, where are we having these fires? We looked at it, and the feedback we got that said is, again, you've saved our life, because we took that class, and that was from work that UL did in 2006. It's like, why has it taken us nearly a decade for us as a state training agency to get this info out? So with a partnership with ISFSI, with Underwriters Laboratory, we provided this to our state. And then we built on that with this other research work, and our folks in our instructional design and development put that into an online class that all of our state's firefighters can take for free. And it's like, well, what if you're not in the state? Then the International Society of Fire Service Instructors has their learning management system as well. And through that partnership, we work with them to put this online for you to take so you could take those classes. Modern construction considerations, improved tactical decision making, and thinking firefighters that come from the Spartanburg burns. So we said, well, we had to make it dynamic so that you can spend as much time on it. And we've had some of our larger fire departments in the state, North Charleston being one. They assigned it to their members through their training system that said, hey, you got to take it. You can spend as little as 3 hours online taking it, or you can spend as much as 8 hours. It depends on how many of the links you click on. It is interactive, it's dynamic, and I've not had one single solitary comment. We've got over 8,000 users in our state, 8,000 users online with this. I've not had one single negative comment. And so that's been a blessing for us. Why did we do the single-family detached dwellings? That's where our fires are. When you look at our information and look at our inference report that you give to us as state agencies, we looked and said, hey, of the residential fires we have, 64% of them are in single-family detached dwellings. So why wouldn't we study that? And you look at this fire and you say, well, that's obvious. Again, back to what Steve was talking about, well, we'd hit that from the front because it's too much work to take a line around to Charlie. Well, why didn't we do that with Delta? If the window's blowing out, fire's blowing out the window on the Delta side of the house, why didn't we do that? Well, maybe we should. And especially if there's a firefighter, and you can see the box on the front of this picture. That's our firefighter. You can see he is off-gassing. He would be grateful to have some water applied to that fire. And so what if he was in the hallway? What if it was in the back bedroom? Those are the things that we wanted to look at that said, do not delay the water. Do not delay the water. If you can limit the air, don't delay the water and control the fire, and isolate yourself or the citizen. The window that you see on the A side of the house over there, you could have sit in that and had coffee during that fire. And the main message I want to give is the fact that offensive and defensive is a strategy, not a position. So as we look back on our research work and we look back to the history books and say, all right, when did we put the word interior into that definition? That's where we try to provide the online training classes that give you that awareness level. We can't train you to fight fire with a computer, and we're not trying to. We're just trying to increase that awareness level, provide it to as many members as we can as possible for free, and allow you to do with it as you wish and as you feel best as you change your fire department. So Dan, I left them plenty of time for questions.
You did.
So see, I did talk fast. Too,
Thank you. So there you see the websites for Shane and the ISFSI information, where they have courses that you can download on modern home construction and collapse, as well as the single-family dwelling fire training. You can get more information on the safety bulletins that Chief Healy was speaking about on the New York City site. Of course, NIST site, we have research information and PowerPoints and things that you can download available. Steve Kerber on the ulfirefightersafety.com site has some of the best training, I think, online in terms of high-quality production interactive training classes on basement fires, structural collapse, vertical ventilation, horizontal ventilation. PPV is coming. It's not done yet, so when you come up for your questions, let's hold off on the PPV questions. And then again, repeating the South Carolina deal. Other work that's going on is movement of hose streams, and NIST is going to be doing some more research on that. UL may complement that as well. So with that, if people have any questions, they want to come up to the nearest microphone, and we've got about 20 minutes to sort of field some questions, and let's have at it.